Okay, I'm going to talk about section 3.4. We're going to do this section in two parts. So this is part one, which will be focusing on concavity and inflection points. This is very much picking up where we left off with talking about whether a function is increasing or decreasing. So this is more sort of graphical qualities of a function. So concavity is basically what it sounds like. And when we look at curves, as long as we're talking about a smooth curve, there's basically four possibilities for a particular interval. One is a function that looks like this, which we would call concave up and increasing. Another one where we have a function that looks like this, so this would be concave down and increasing as well. A function that looks like this, which is concave up, like this one, but it's decreasing. And then finally, a function that looks like this, which is concave down and decreasing. As far as when we say concave down or concave up, if we're talking about a curve, a line doesn't have any concavity at all, but if we're talking about something that has a bit of a curve to it, if you look at this as kind of like a satellite dish, is it mostly sort of pointing up or is it mostly pointing down? So these two would be concave up, these two would be concave down, okay? So this is something that we can determine using derivatives, which we'll talk about here. So first of all, let's start off with what we already know. So both of these functions are increasing. So we know that if a function is increasing, so we would say f is increasing, and of course, we know that means f prime is greater than 0. So even though these curves look very different, both of these f prime is greater than 0. Over here, both of these functions are decreasing. So f is decreasing, which we know that means that f prime is less than 0. Okay, now for concavity, it's a little bit more confusing. We actually think about whether the slope itself is increasing or decreasing. All right, so let's think about that, whether the slope itself is increasing or decreasing. So I will tell you in a case of a function that's increasing, it's easy to tell if the slope is increasing or decreasing. So for instance here, if you look, my slope is getting steeper in a positive direction. So if I want to give that values, and I'm just throwing this out here, I could call that a slope of 1. I could call that, let's just say, a slope of 4, slope of 8. So that's clearly increasing. Over here, okay, we have a slope that is decreasing. Okay, so this slope is increasing. This slope is decreasing. So slope is increasing. This would be slope is decreasing. All right. So slope, of course, we're talking about f prime, right? That's what gives us slope. So if we want to know the slope of this function, let's put this in terms of calculus. This is going to be f prime is increasing, and this is going to be f prime is decreasing. Now here, I will tell you have to think about the fact that since these slopes are negative, it actually goes in reverse, excuse me. So in other words, if I'm going steeper negative to less steep negative, my f prime is actually increasing. My slopes are actually increasing, which can be a little confusing. Because if we think about like this slope, I don't know, let's throw a number on it. Let's call it negative 10. That'd be like negative 4, negative 1, negative 1/2. Since we're going from steep negative to less steep, f prime is actually increasing. So f prime here is increasing. The slopes are increasing, right? Now here, we have the opposite. We start with something, let's say negative 1/2, negative 1, negative 6, negative 8. Those values are actually decreasing, right? Because they're getting more and more negative. So when f is decreasing, when f prime is negative, f prime is decreasing when we are getting steeper. So f prime is decreasing. Now, as you can tell, this kind of gets confusing. You may explain this to you. I really have to think about what I'm talking about. But luckily, we can look at this connection and it becomes a lot clearer. So whether or not f prime is increasing or decreasing has no bearing on whether f prime is positive or negative. Okay? What it has bearing on is this concavity situation. So notice I line these up. If we are concave up, so both of these are concave up, our f prime is increasing. Now, if we think about that, if I tell you a function is increasing, what do I know? I know its derivative is positive. So in other words, we're going to be looking at the double derivative, right? So we're looking at the derivative of the derivative. So up until now, we found double derivatives, but we haven't talked about some applications of them very much. So here we realize that it relates to this concavity question. So f prime is increasing means f double prime is greater than 0. So when we're looking for intervals of concave up or concave down, we're going to be looking at the double derivative. If we're looking at whether a function itself is increasing or decreasing, we look at the first derivative. And then over here, as I was talking about, both of these are concave down. So f prime is decreasing in both these cases, concave down. So like the satellite dish is pointing down. So f prime is decreasing, which means f double prime is less than 0. So that's really going to be our focus today. And so let me erase and then we'll formalize this. Okay, so let's get this in our notes. This is going to be very similar to the way we analyze f prime to determine whether a function is increasing and decreasing, and also whether we have relative max and mins. This is going to be very much like that, except we're talking about concavity. The big difference here, instead of analyzing the first derivative, we'll be looking at the second derivative. So if f double prime is greater than 0 on the open interval a to b, then f is concave up on that open interval. Notice we don't have the same thing we have with intervals of increasing, because with that one we could actually go with the stronger statement here. It's open interval to open interval. It actually makes these things a little bit easier to deal with. If f double prime is less than 0 on the open interval a to b, then f is concave down on the open interval a to b. And then finally, this sort of takes the place of our relative max and mins for the first derivative. We're going to talk about what are called inflection points, or sometimes they'll be referred to as points of inflection. Makes no difference. So given f is continuous at x equals a, f has an inflection point if f changes from concave up to concave down, or vice versa at x equals a. In other words, f double prime changes sign at x equals a. So the way we go after these is very similar to relative maxes and mins. So if you remember when we do relative maxes and mins, we find when the first derivative is equal to 0, or perhaps doesn't exist. If the derivative goes from positive to negative, we know that's a relative max. If the derivative goes from negative to positive, we know it's a relative min. Inflection points, there's no like relative min or relative max. It's just anytime we see the concavity change from concave up to concave down, or vice versa, we call it an inflection point. So really what we're just looking for is that sign change for f double prime. And the way we go after that is we're first going to start with f double prime equals 0, or does not exist perhaps. Okay, so let's do some examples of finding these intervals and also these points of inflection. And basically what we're going to see is something very similar to what we saw with the first derivative analysis. Okay, for the rest of our examples here, we're going to be doing the same for each. So we're determining the x values for inflection points, and also the intervals, of concave up and concave down. We start off example 1 with a polynomial. Once again, we like polynomials because they're what we call well-behaved. They're always continuous, they're always differentiable, so it makes life really easy. It's a good place to start. Okay, so since we're talking about concavity and inflection points, we go right to the double derivative. If we were talking about intervals of increasing and decreasing, or relative max and mins, critical points, things of that nature, we use the first derivative test. So first, let's take the derivative, 12x to the 5th plus 15x to the 4th, okay? And then take the derivative again, and that would be 60x to the 4th plus 60x to the 3rd. And just like with the first derivative, we're interested when this could possibly change from the double derivative from positive to negative, because that's going to determine concavity shifts and inflection points. Or we could also have this when f double prime does not exist. Of course, with a polynomial, we never have to worry about that either for the first derivative or the second derivative, or any derivative for that matter. Okay, so we want to solve this. The easiest way to do this, I think, is factor out of 60 x to the third, which is going to leave me with x plus 1 equals 0. So that gives me two potential, and these are potential. They're not like critical points where we already determined there's something. These are potential inflection points, which I'll talk about. That's kind of a common error, as people will automatically say they're inflection points without testing whether or not the sign changes. So the way I'm going to do this is just like I do with the first derivative. I'm going to do a sign chart here. So I'm going to put 0 on there, 1 on there. I have two factors. The 60 doesn't really matter. That's positive. So I have x to the third as one of my factors and x plus 1. If you want to put the 60 in there, go for it. Remember, with these sign charts, all we care about is whether the value is negative or positive. Now we're going to pick test points. So I'll pick -1, 0, 1, 1/2. We're not going to do any better than that. And so we're just going to plug these in. So this was going to give me a negative. Plug that in. Oh, shoot. I did this wrong. -1. Let me flip those. Let me start over. So this is -1 and 0. Let me fix that. Actually, so this will be -2. We can call this -1/2, and this is 1. Okay, let's try that again. So this will be negative, this will be negative, negative times a negative, that will be positive. Okay, -1/2, so that's negative, that would be positive. So this is negative, positive, positive, and positive. Okay, so this tells us everything we need to know. We're concave up. So concave up, you'll see me abbreviate like this. CCU, concave up. That is -infinity to -1 and 0 to infinity. And that is because f double prime is greater than 0. Concave down. -1 to 0, and that is because f double prime is less than 0. Okay? And finally, inflection points of x equals -1 and x equals 0. And specifically because f double prime changes sign. It does not matter whether it goes from positive to negative or negative to positive once we get that sign shift. So graphically, probably I should mention what these things are going to look like. You know, if I look at this without getting into, it's going concave up to concave down to concave up. So this would, and I don't know what the function looks like, but this is what a concavity shift will look like. So concave up, concave down, concave up, the inflection points are in between. Okay. There will be functions where we do all of the analysis. We'll start with the first derivative, do the increasing, decreasing, then we'll go to the, yeah, it definitely doesn't look like that. Then we'll go to, you know, relative max and mins, and then a double derivative for the inflection points and concavity. All right, let's get to a function that's a little bit more complicated here. Okay, so now we go to a function that is not a polynomial. It is going to be continuous and differentiable. E to the x, we're generally not going to have any continuity issues. We can plug anything in there. We don't see the zeros in the denominators. We're not seeing logs, we're not seeing even roots, so we can go ahead and analyze this. Now, before I do that, let's rewrite this in a way that is going to be better for taking derivatives. So realize this is -4e to the -1/8 x squared. Okay, so let's take the derivative. So we'll just keep the -4 out front. We can simplify when we need to analyze. So we're going to blob this out. The derivative of e to the blob is e to the blob, and then don't forget we have to take the derivative of the blob. So that 2 is going to come down there. That's going to give me -1/4 and then x. Okay, so now I'm going to take the double derivative. So let's simplify this. So we have f prime of x equals -4 times -1/4. That'll give us a +1. So I'm left with x e to the -1/8 x squared. Okay. Now I'm going to take the double derivative. Now one thing I want to point out is Not only do we have to do chain rule with this one, because we still do have the composite function, but we have to do product rule, because we have a product here. So let's take the derivative of x first, that's 1. Copy down e to the blob. Okay. Plus, now copy down the x, let's take the derivative of e to the blob. So that would be e to the blob. And then the derivative of the blob, which 2 comes down, that's going to give us negative 1/4, and then x. Okay, so I'm interested when this is equal 0. Okay, now don't get too hung up on how awful this looks. We can do a little, you know what, let's do a little, you know what, let's do this. So what I want to point out is that we have this e to the negative 1/8 x squared in both terms here. So I'm going to start off by factoring that out, which I think is going to make this a lot easier. So we're going to get e to the negative 1/8 x squared. Now what that leaves me with, right, it leaves me with, that whole thing comes out, so that's 1. So since we have positive things times a negative, let's just make this minus. If you have to put an extra step in here, you know, that's fine. And then this is going to be 1/4 x squared equals 0. So now we're in that realm of using the zero product property. E to anything is never 0, never ever 0. So this one is not going to give us any zeros. So it's just this one here. So I'm going to get 1 minus 1/4 x squared. I want to know when that's equal 0. So let's move this around. So 1 is equal to 1/4 x squared. Multiply both sides by 4, we get 4 equals x squared. So I have 2 potential inflection points, one at negative 2 and one at 2. So let's put that on the number line. So negative 2 and 2. So negative 3, 0, and 3. Okay? So now, let's see. You know, here's the thing about this. So this is my derivative. This whole thing here is, this is my derivative. Let me point out that e to anything is positive. So let's not include this in our number line, because this isn't going to change the sign. It's always positive. If it was always negative, I want to put the negatives up here. So really the only thing that's going to impact whether my double derivative is positive or negative is this term here. So let's put that in there. 1 minus 1/4 x squared. So now if I plug negative 3 into that, that's going to be 9. 9 times 1/4, so that'll be 9/4. So that's greater than 1, so this is going to be a negative. If I plug 0 into that, I just get 1, that's a positive. If I plug 3 into that, I'm getting the same thing I got here because we're squaring it, that's a negative. So, you know, even though it was really ugly, in the end, it wasn't that hard as long as I sort of thought through it. So that means, and I'll try to fit this in here, we have inflection points at x equals negative 2 and 2, and that is because f double prime changes sign. Oh boy, I'm running out of room here. So let's see. Okay, so you still have that. So we're going to be concave, what was it? Negative, negative, right? Positive. Okay, so we are concave up from negative 2 to 2, and that is because f double prime is greater than 0, and we're concave down from negative infinity to negative 2, and then 2 to infinity, and that is because f double prime is less than 0. So hopefully this isn't too ugly, but that's it. That's our double derivative. Okay, I'm going to do one more example, and then that will be it for this video. Okay, last example today, I wanted to go with a function that we know what it looks like, and it kind of has an odd quality. Right off the bat, we should recognize this, and this is true, you know, if we're doing intervals of increasing or decreasing. It's also true with concavity. Look at those domain issues and make sure we're not including any domain issues. So our domain here is all reals, but we have to throw out x equals 0. X equals 0 cannot be an inflection point. It cannot be included in an interval of increasing, decreasing, concave up, or concave down. Okay, so now from here we're going to do our analysis and just sort of star this somewhere. One thing you might want to do, just like we do with the first derivative, you might want to put that in your number line right away, reminding you that it's not going to be part of our analysis so we don't forget. So okay, so let's call that x to -1. So y prime will be negative x to the negative second. Okay, y double prime is going to be bring down that 2, excuse me, negative 2, so I'll give us positive 2 x to the negative third. So I get 2 over x to the third. Now the first thing I always do with our critical points is we want to look when this thing is 0. This, of course, is never going to be 0 because if I have a fraction equals 0, that means the numerator is equal 0. Now, what I also would do, just like I do with critical points, is I would consider when the denominator is 0. So the double derivative doesn't exist at x equals 0, but let me point out that cannot be an inflection point because it's not in the domain. If it's not in the domain, if it's not continuous, it can't be an inflection point. So that means I have no inflection points. There's no potential if there's no place the derivative is equal 0 or it does not exist. Okay? Now, this does not mean that the concavity doesn't change, which I'll talk about. Now, we do have an issue at x equals 0. Let me point out, if this was a continuous function, which this is not, but if it was a continuous function and we had no inflection points, and we would see this like with a parabola, it's either going to be always concave up or always concave down. So at that point, all I would do is plug in a single value into our double derivative to determine whether it's positive or negative. Okay, but here we do have this concavity issue. So I'm going to treat this just like I would, you know, a normal sign chart. Plug in -1, plug in 1. My double derivative here is 2 over x to the third. So if I plug negative into that, keep in mind odd powers, we retain that negative. 1 goes in, that's positive. So that tells me what we need to see here. And so what we have is we are concave down, negative infinity to 0. And that is because y double prime is less than 0. We are concave up, 0 to infinity, and that is because y double prime is greater than 0. So we do get that shift in concavity, but since x equals 0 is not in the domain, we do not have an inflection point. And of course, this is one I chose because we know what this looks like, right? It looks like this, and this confirms what our analysis is showing us, right? Concave up from 0 to infinity, concave down from negative infinity to 0. Okay, so that's video 3.4, part 1, concavity inflection points.